everybody, and welcome to the Open Orbit podcast. Today, we are joined with Dr. Zach Berta-Thompson. Zach is an astronomy professor at the University of Colorado Boulder, using both ground-based and space telescopes to look at exoplanet atmospheres. He views each exoplanet as a laboratory experiment that can help us understand all of the phases an exoplanet goes through. He comes up with ways to carefully predict whether life exists beyond our solar system. Zach studied with leading astronomers at Princeton, Harvard, and MIT, and became a professor in Colorado in 2016. And he leads a team of researchers and teaches students how to use curiosity, creativity, coding, and kindness to learn more about how worlds work. Hi, Zach. How are you doing today?
Hi, Hunter. I'm great. Thanks for having me.
Awesome. I'm very excited for this episode. Zach was actually my first ever astronomy professor here
Oh,
at
yeah.
CU Boulder for Astronomy 1030.
Right. And the listeners should know Hunter was an excellent student in that
Oh,
class.
I tried to be.
Um,
It was
okay.
one of the classes that was like, yes, this is definitely what I want to do.
I'm glad
Yes.
that was my goal.
Yes. And Zach is a great science communicator, so I'm especially excited for him to be on today.
Hooray.
Awesome. So, okay, so your thing is exoplanet atmospheres.
Yes.
So, and you call yourself an observational astronomer. Can you tell us what is an observational astronomer? How is that different than any other type of astronomer?
Sure. Yeah. So, by an observational astronomer, I mean that I use telescopes combined with math and physics and various other tools to observe the universe and learn new things about it. I think the other way you could be an astronomer or an astrophysicist, that's kind of synonymous, would be generally you could be more focused on a theoretical side of I'm going to work from basic principles and come up with models for how things work. As an observer, I like to get to a telescope and look at the sky and learn some new things about it.
Awesome. And you're going to be teaching my class next semester
I
too
am,
on
yes.
observation.
I'm going to train you to become a
Yes.
better observational
And I'm
astronomer.
very excited on that.
This will be fun.
Let's get into some exoplanet stuff.
Sure.
What is an exoplanet and how is an exoplanet different than any other type of planet?
Yeah, so exoplanet is a name that we made up that's a short version of extrasolar planet. So just like extraterrestrial intelligence would be like aliens from beyond Earth, extrasolar planet means a planet from beyond our solar system. So most of the planets that folks are familiar with are the 8 major planets and lots of other kind of mini planets within our solar system, all orbiting around our sun. An exoplanet is exactly the same as those, it's just they orbit other stars.
Okay. So, what classifies a planet?
Oh, yeah, like what makes Wally not a planet
Yeah,
and Earth a planet?
exactly.
Yeah. Okay. So it's a fuzzy line. In some sense, a planet is just an object that orbits around a star. But the major planets are ones that are big enough that they have enough gravity that they kind of get squished into a sphere. If you just have a rock floating in space, technically, I think you could call that a like itty bitty, teeny tiny dwarf planet. But when we say planets, generally we're referring to these major things that are big enough to basically be spheres. And then there's this weird other technical detail that kicked Pluto out of being a major planet, that we like major planets to be ones that have strong enough gravity that they kind of clear out their orbital space around their stars. So Pluto is a big round thing that is orbiting around the sun, but there are lots of other big round things orbiting around the sun out there as well. It's just not quite big enough to kind of throw out all of the things that would be in similar orbits around it, the same way
Yeah.
that giant planets do.
So, you specifically study exoplanet atmospheres. You find exoplanets and you look at their atmospheres to see more information about that exoplanet and what the conditions on it could be.
Yeah.
How do you detect an exoplanet?
So the challenge with exoplanets is because they orbit other stars, it's the same difference between some other star and the sun that also applies to their planets. So think about going outside on a sunny day and feeling the heat from the sun in your face. You are receiving light that's coming from the sun, our very nearby star. And then think about going out on a cold night and seeing a tiny, cold little pinprick of light in the sky that is some very distant star. That's because it is the same kind of star as the sun. It's just light years away. And so we receive a tiny, tiny fraction of the same amount of energy from it. And so, likewise, the planets that are orbiting around that distant star receive a tiny amount of light from them, and they're so close to their star that it's hard to just like take a picture of it. So, it's like really we're looking at an point of light that is so far away, and we have to come up with various subtle tricks to figure out whether that planet is there and what its properties are like.
Okay, and what are those things that you can figure out through looking at an atmosphere of an exoplanet?
Yeah. Sorry. So for studying, one of the tools that we use to just see a planet in the first place, whether or not it has an atmosphere, is this method called the transit method. So we watch the brightness of a star. This is a thing that astronomers have gotten really good at, measuring the brightness of a star very, very precisely. And maybe, just maybe, once per year for a planet, or its year, a planet will pass in front of its star and block a tiny fraction of that star's light. And so if you measure the brightness of a star very carefully, you can see this little dip as the planet transits in front of its star. And so by measuring how much light the planet blocks, you can learn how big the planet is. And so, let me turn this around. Will planets all have the same, will one planet be the same radius in every kind of light that you look at it?
Oh, no,
Why,
absolutely not.
why not?
Because some light is opaque to certain atmospheres
Yeah,
and
exactly.
certain gases.
Right. Yeah, exactly. So that's the trick, that one trick that we can use to study these planets' atmospheres,
Mhm.
is that we can say, okay, if this were just a ball of rock, the shadow of a ball of rock is going to be the same at every wavelength of light, every color of light, whether we look at blue light from like 400 to 500 nanometer wavelengths, or red light from 600 to 700 nanometer wavelengths. It's just a circle passing in front of another circle, and it would have the same size. But as you said, if there's an atmosphere surrounding this planet, then that atmosphere will be transparent at some wavelengths and opaque at other wavelengths. And so the planet will look a little bit bigger at some wavelengths and a little bit smaller at some wavelengths. And so you can tell, oh, there's an atmosphere there, and even what's in it, based on how the size of the planet seems to change looking at lots of different wavelengths of light.
Okay, so we've said the word wavelengths a lot, and that's
Yeah.
something that I think is it's something that we will probably continue to say a
Yes.
lot on this podcast. So how do we describe wavelengths?
Yes, thank you so much. So this is one of the ways that we talk about light, is as a combination of waves. And I think a good analogy, like when I say wave, what do you think of?
I think of ocean
Exactly.
waves.
Yes, I think of ocean waves. So you can think of light that we receive from any light source as energy that's being transmitted to us on waves that are like ocean waves in a lot of ways. And sometimes at the ocean, you see lots of really big waves that have these long kind of stretch between them. There's like a wave, and then 30 seconds later, there's another giant wave that comes in, and another giant wave that comes in. But you can also look at the kind of ripply, heavily textured surface of the water, of these tiny little ripples that are like maybe only a centimeter in size. And so the surface of the ocean is a combination of all of these waves of different sizes, from itty bitty tiny ones to these huge, gigantic ones. And the roar of the ocean that you hear, like sound wise, is a combination of all of those waves. And as you listen to it, you can't necessarily pick up, oh, this is how many big waves there are and how many little waves there are, but you're hearing the combination of all those smushed together. And so the same thing with light, our eyes can like get a very coarse sense of the wavelengths of light that are present. Like our eyes are sensitive to waves of light that have wavelengths between 400 and 700 nanometers. That's really, really tiny. Like it's so tiny that it's weird to think about them as waves, but they are itty bitty tiny waves. And our eyes get a sense of overall, okay, this is how much light is coming at me. I know how bright it is. It's like, that's brighter, that's dimmer. And we have a sense of like, oh, there's a little bit more longer wavelengths. It looks a little bit redder, or there's a little bit more shorter wavelengths. It looks a little bit bluer, but that's about it. But astronomers, observational astronomers, can use a tool called a spectrograph that allows us to look at all of the individual wavelengths of light that are present and see how much of each one of them makes up any light source that we're seeing. And sometimes it's like, it's about the same of everything. And sometimes it's like, oh, there is so much of this one particular wavelength. There's so much 656.3 nanometer, meaning there's lots of hydrogen there. And so by looking in detail at these, you can learn about the composition of any particular gas and how it interacts with lights and such.
So a wave spectrum, like all of the waves that light emits, is like a giant rainbow, but we can only see this like very small portion of the rainbow from red to blue. And each color in between red and blue that we see, orange, purple, green, all of those are different wavelengths. But astronomers like you can use these really fancy instruments to look at light that we can't see with our eyes. And different light is emitted by different chemicals. So we can see things about chemicals or things about an atmosphere from this light that we see on
Yes.
your spectrograph.
Yes,
Great.
exactly. We can both sense wavelengths that we can't see with our eyes, and we can measure much finer detail of wavelengths of light that we can see with our eyes.
All right. So we've talked about exoplanets and how to detect them. You were specifically looking at atmospheres around exoplanets. What is an atmosphere?
That is a very good question, and one I struggled with in a recent paper I was writing. At its core, an atmosphere is gas that is surrounding a planet and is gravitationally bound to that planet. It's not just zipping by, it is attached to that planet by gravity.
I understand Mercury does not have an atmosphere, but then we have other planets like Venus or Jupiter that have really, really thick atmospheres. What determines how thick an atmosphere is, and how do atmospheres vary in that way?
Yeah. So Earth has a 1 bar atmosphere. Our unit of pressure, easy unit of pressure is bars. So Earth has 1 bar atmosphere. It's nitrogen and oxygen that mostly comes from plants and microbes. Venus has like very roughly 100 bar atmosphere that is mostly carbon dioxide, way thicker atmosphere. Its surface pressure is so high that you would be crushed if you were at the surface of it. It has very strong greenhouse effect. Mars has a really thin atmosphere. We'd still say it as an atmosphere that is like 1/100th of a bar. But Mercury and the moon, there are like a few little gas atoms and ions zipping around on the outskirts of those planets, but we wouldn't say that they have an atmosphere. Technically, they have a surface pressure that is, I don't know, 10 to the minus 14 bars or something, but really that means there's practically nothing there. And so you can have atmospheres that come in a variety of thicknesses or kind of characterized by their surface pressure. But what exactly sets the line of this is an atmosphere that, or that this is not an atmosphere is kind of a fuzzy thing.
Great. Okay, so one of the most exciting things to me when I think about exoplanets is finding Earth like exoplanets and
Yeah.
finding potential signs of life.
Yeah.
So, how common are Earth like planets out there?
Ooh, that hyphen like is carrying a lot of weight there. What exactly do we mean by Earth like is a like really big question. What do you mean by Earth like?
I guess when I think of something that's like Earth, I think of something that has liquid water, an atmosphere, and potential for life.
Yeah. All right. So then my answer to your question is I have no idea. The like a thing that we can measure for lots of planets is how big is the planet and
Hmm.
how far away does it orbit from its star. And that says nothing about what the world is actually like. It could be a total barren rock or it could be a rich lush biosphere. And so for that there's about a half an earth like earth size earth temperature ish planet per star in the galaxy.
Oh,
So
okay.
like if there are about 100 billion stars in the galaxy, there are, I don't know, 50 billion planets that are about the right size and temperature that you could imagine being kind of Earth like.
Okay. What are the other variables that make it so hard to determine whether that's Earth-like planet or not? Like, in if it exists in this perfect distance from the sun,
Yeah.
and it's a okay size
Yeah.
to have like an active core, what other things makes us unsure of the conditions?
Yeah. Good question. I've hidden a sneaky fact here, which is a statement that we make about how many planets there are that are about the right size and at about the right distance from their star so that you could have a temperature that's about right for liquid water. That's a statement that's mostly based on stars that are much smaller and cooler and lower luminosity, so like much dimmer than the sun. So our sun is compared to the kind of typical star in the galaxy, pretty massive and pretty luminous and really bright and hot. Most of the stars are a lot cooler and smaller. And it's easier to find planets around those. And so we found lots of planets that seem like they could kind of fit this bill of, yeah, maybe that's an Earth like planet, except for this big question that we don't know how those planets interact with their very different stars. I think I'm pretty confident that if you gave me an Earth-sized planet in an Earth-like orbit around the sun, I'd be like, yeah, it's probably pretty Earth-like. But as soon as you put that around a star that is very different from our sun, I'm less certain. And the big reason I'm less certain is that these small, cool stars are also just like way more, weirdly enough, way more like tempestuous than the sun. And so they emit less light overall. And so your planets can be kind of closer into them. And that seems like that would be fine. But these stars also mysteriously emit lots of X-ray light and ultraviolet light and flares and have crazy magnetic fields. And so there are all these ways that they could erode a planet's atmosphere, so that before you even get the chance of asking, is the temperature right for liquid water, you have to ask, oh, could this planet hold on to an atmosphere at all? Or did its star strip it away?
And yeah, it's really cool. I've heard of super Earths, I've heard
Mm,
of hot Jupiters, and I've heard of sub Neptunes.
yes.
Can you explain what those are? Those
Made
are
up
all
words.
different. Okay. So how do we use them? And
So they're made up words that are kind of useful analogies that we can
okay.
latch onto. That we have these 8 major planets in the solar system that we're kind of familiar with. So the first of these we started using was hot Jupiter,
Mhm.
which was we started astronomers started finding planets around nearby stars that seemed at the time seemed really weird and surprising. It was like, that's a planet that seems to have the mass and size of Jupiter, but it's orbiting around its star way too close to be like actual Jupiter. It's orbiting around its star once every like 3.5 days. That means it's so close that it's only like, oh, if you were standing on this planet and you looked up at the sun would like take up like a quarter of the sky or something. It's like, and so these planets that are so close to their stars are so um brightly illuminated by their stars that they're just really, really hot. And so the simplest name we have for them is a Jupiter-sized planet that is really hot is a hot Jupiter.
Okay.
And then super Earth and sub Neptune is really pointing to this absence in our own solar system of planets that are intermediate in size between Earth, which is 1 Earth radius, and Neptune, which is like 3.9 Earth radii. If you have a planet that's 2 Earth radii, say right between those, without studying exoplanets, we wouldn't really have a sense of what that planet is like. It could be, maybe that's just another ball of rock like Earth with this tiny little veneer of atmosphere on top of it. Or maybe that's effectively a gas ice giant like Neptune that has a solid core, but then like a big chunk of its radius is made out of this thick hydrogen helium envelope on the outside. And so super Earth is a thing that is bigger than Earth, and sub Neptune is a thing that is smaller than Neptune. You could call Earth a sub Neptune, and you could call Neptune a super Earth, but they're words that we use to describe this kind of like filling in the population and size between the those two limits that we have in the solar system.
In your research, you are looking for biosignatures as well. Is that correct?
Right now, there's no planet that I have like observations planned that are like we're going to tell whether or not there's life there. But
Hmm.
that's a long-term goal. Yes.
Okay.
Like what planets have atmospheres? Are those atmospheres conceivably habitable? Does a planet with a habitable atmosphere have life on it? Can we see evidence of that life?
How do we determine what a biosignature is if life on a different planet could be different than life on Earth?
Right. Yeah, yeah, yeah. Ooh, oh, that's like a bazillion questions in one. So the like a biosignature as a just as a basic idea is some piece of evidence that points to this planet having life on it. When we're talking about exoplanet biosignatures, we're talking about a signal that we could detect from that planet that tells us that there is global life on there. If there were like some one tiny microbe that lived in a cave somewhere deep on that planet, we're not going to see that with a telescope from far away. And so, practically, many biosignatures that we talk about are atmospheric biosignatures. So, the presence of molecules in a planet's atmosphere that we think can only come from life. Do you have any ideas of like what are molecules on Earth that come from life?
Carbon dioxide.
Carbon dioxide comes from us. Yeah, so on Earth, many of our molecules are produced by life.
Hmm.
One really important one is oxygen, is O2, comes from plants and photosynthetic microbes. So through the process of photosynthesis on Earth, light from the sun combines with water and carbon dioxide and produces oxygen. And in the specific settings of Earth, if you took away life on Earth, if you took away plants and photosynthetic microbes, we would have like the oxygen in our atmosphere would disappear pretty quickly. And that would be bad news for creatures like us that like to breathe oxygen, and our atmosphere would look very, very different. And so you could think of that as a little bit of a biosignature, that like the presence of oxygen in Earth's atmosphere points to the existence of photosynthetic life. Over the past decade or so, as we've gotten kind of tantalizingly closer to finding planets where maybe we could study their atmospheres and maybe be able to see, ooh, there's oxygen in there or not, we've gotten better at understanding planetary atmospheric physics. And it turns out there are lots of ways that you could fill up a planet's atmosphere with oxygen that don't rely on photosynthetic life. And so by itself, it's probably not a great biosignature anymore. Maybe if you ask somebody 30 years ago, that's how we look for life. We look for oxygen on other planets. Right now, if you ask somebody, they would say, "Oh, no, not the way to do it." But what we think about kind of more generally in terms of biosignatures now is we look at the chemistry of an atmosphere, its complete inventory of molecules, and we ask, is that a combination of molecules in the right abundances that can be created abiotically without the presence of life? Or do we require life to create that? Do we need photosynthesis making some of these molecules? Do we need some sort of weird biochemistry to get things in these exact ratios? And so that's a fuzzy thing. And it depends a lot on, we have to be able to rule out all other atmospheric physics that might be able to produce this particular suite of molecules in an atmosphere to be able to say, the best explanation I have for this planet is there's some kind of life there.
The main reason I ask is because the first life that existed on Earth, we
Yeah.
believe, did not breathe oxygen. They breathed methane,
Right.
and oxygen was actually toxic to
Yeah.
them until we had some climate crisis, and then oxygen started filling their atmosphere, and only organisms that could tolerate that oxygen was able to thrive afterwards.
Right.
So you mentioned oxygen alone is not the best indicator of life being on a planet. So how do you determine what kind of molecules can exist in an atmosphere that specifically come from life versus abiotically from lifeless processes?
So you're asking like how do we find the aliens?
Yeah.
Um I don't know, Hunter. I don't know. So planetary atmospheres are really complicated. And so there is it's this huge field of lots of folks working on steadily marching forward with new observations of atmospheric evolution, both within the solar system and beyond the solar system with exoplanets, and new theoretical models of how atmospheres respond to different environmental conditions, and the chemistry that happens. And this kind of working back and forth between, we learn something new from the observations, we have a better theoretical model, we iterate back and forth, and we're constantly trying to improve this. And so our job as exoplanet astronomers, both observational and theoretical, is to try to advance our theoretical understanding of atmospheric physics to the point that we understand atmospheres so well that if we look at a really good observation of an exoplanet atmosphere, we could say, we can rule out all of the possible kind of geological and geochemical ways that you could produce these molecules. There's this weird feature there, this presence, like carbon dioxide and methane and oxygen in the right ratio that is hard to explain any other way. So that's like process of elimination. There's another way that is a little grimmer, I guess, which is a great biosignature would be chlorofluorocarbons. Like a lot of industrial pollutants are great biosignatures, things that you need intelligent life and civilizations to make, that you could potentially see in an atmosphere. Unfortunately, if you were to look at a planet and see its atmosphere, see an atmosphere that is so full of that you can see it across interstellar distances, it probably means that something has gone horribly wrong and they've destroyed their ecosystem. But we don't know. So there's it's this constant search for what could be potentially reliable indicators of life, either current or past, on the
Okay.
planet.
You were talking about the very red part of our spectrum,
Yeah.
and you mentioned to me before we started recording that infrared light is
Mhm.
particularly important for atmospheres, exoplanet atmospheres. Can you tell us more about that?
Yes. Yeah. So if you imagine looking at a rainbow, you see this. There's the kind of like the violet, blue, green, yellow, orange, red. It keeps going beyond that. Your eyes just aren't sensitive to it anymore. So if you had eyes that were sensitive to longer wavelengths of light, just through whatever accident of evolution, then you would be able to see rainbows that can continue to much longer, redder than red wavelengths of light. And so that infrared light beyond red is super important for our atmospheres for two reasons. One, lots of molecules that we care about in atmospheres absorb really strongly in infrared light. So, hydrogen, carbon dioxide, methane, these are all things that have very strong absorption features in the infrared. The other reason is that if you go to really long wavelengths of infrared light, the you start to see emission from like light emanating from relatively cool surfaces. There's ooh, wait, do you why does the sun emit visible light?
Because it is a black body that emits across all wavelengths, and visible light is just part of that.
Yeah. Oh yeah, yeah. All right.
Is
Ooh, all
that is
right.
that the answer you're looking for?
Yeah, yeah,
Okay,
yeah, yeah. So
great.
yeah, yeah. You use some Astro 1030 jargon here. Yeah, sun emits light at all wavelengths. It emits the most light at visible light wavelengths because it's really hot. So because it is 6,000 Kelvin in temperature, I don't know what that is in Fahrenheit or Celsius, but 6,000 Kelvin, it's hot. That temperature means that it emits these short wavelengths of light that are 400 to 700 nanometers. There's lots of visible light that comes from the sun. Cooler surfaces, so like the surface of our planet, is Earth's surface is about 300 Kelvin. That's about 20 Celsius or something. That's like room temperature. That 300 Kelvin temperature emits the most light in the infrared. Instead of emitting in the optical, it emits in infrared wavelengths. So instead of at 500 nanometers, it emits at 5,000 nanometers or 10,000 nanometers. And so those really long wavelengths of light tell us about the temperatures of surfaces that we care about for planets. So if we want to study stars, we use optical light. If we want to study planets, it just helps to use infrared light.
And incidentally,
Yeah.
JWST uses infrared light. So,
Exactly.
yeah, can you tell us more about what JWST is doing right now for exoplanet detection and discovery?
Yeah. So JWST is this amazing new 6.5 meter space telescope it's so like the fact that it's 6.5 meter diameter for its mirror gives it this extraordinary power to collect light from very faint things. It's so big they couldn't like launch it like that. They had to fold it up and put it in a rocket and then put it in space and then unfold it. This like amazing feat of engineering. So with this extremely sensitive telescope that's designed to study infrared wavelengths of light, it allows us to detect the light that is emanating from cooler objects and surfaces. So like planets. With the Hubble Space Telescope, which was incredible, like one of my very favorite telescopes in the solar system, I guess, we could only observe basically optical wavelengths, visible wavelengths of light. With JWST, by observing in the infrared, we can see the thermal emission from planets themselves. And so there have been these series of observations that astronomers, including my group, have been doing, trying to detect the light that is coming from the planets themselves. We're not just seeing like a planet pass in front of its star and there's this little shadow where the starlight disappears. We're watching when the planet passes behind its star. And so the light from the planet disappears. And at visible light wavelengths, the planet doesn't emit any light at all, practically. But at infrared wavelengths, the planet is glowing. It has this like infrared light streaming off of it. And so when you see a planet pass behind its star, that tiny amount of light that the planet emits disappears. And so that means you can measure it briefly, and figure out how hot that planet is.
Great. So viewers can go to NASA James Webb Images
Mhm.
online, and they can see pictures of Jupiter, which has been taken in infrared, but we were actually able to see it in visible light. We can actually see a real image of it,
Yeah.
and as well as Neptune, I believe.
Mm.
But when we're looking at exoplanets, we're not looking at these like pictures. We're not able to see a picture of a planet. We're seeing the spectrum of light that you've been talking about. And one of the new exciting missions that is going to happen in the future, if all goes well, is the Nancy Grace Roman Space Telescope, which is going to be also looking for exoplanets, but with many different methods of looking at it, not just spectroscopy. But what are you looking forward to most with the Nancy Grace Roman mission?
Yeah. So the Roman telescope is this incredible telescope that's been built. It exists, has these amazing detectors on it. It's a telescope that was 30 years in the making. It's like there's a whole look up the history of the Roman telescope. It is amazing. And whether or not it launches depends on the NASA's budget for the next year. So it's a very scary thing that in the investment of many people's lives is really on the line right now. But if it launches, Roman will be able to do two really cool new things for exoplanets. So, one, it will have a coronagraph on it. This is a tool that allows you to do the incredibly hard thing of picking out the little point of light coming from a planet next to its very bright star. And this is the way that we can actually in the future. This is how we will have to find truly Earth-like planets around sun-like stars. The only hope of doing it is this particular method. And so the Roman telescope is our first pathfinder in that direction. The other thing that Roman is going to do is search for planets through microlensing, gravitational microlensing, so it has this, it's like the Hubble telescope, but with 100 times the field of view. So it gets to just stare at the sky at this incredibly high resolution, incredibly precise measurements. And if you watch millions of stars at the same time for months, just stare at them continuously, you might see one dark little planetary system happen to pass in front of a much more distant star, and through Einstein's theory of general relativity, bend space and time in such a way that it becomes a magnifying lens that magnifies the brightness of that background star, causing this flash that allows you to pick up the presence of that planet and infer its basic properties. And so this is the way that we get to learn about the outskirts of planetary systems, what kinds of other Uranuses and Neptunes and Plutos are out there around other stars. So it's this kind of expanding our horizons for understanding planets in these really important dimensions.
Out of the two, which one do you think is more critical for exoplanet science, or do you think it's a combination of them both working together?
Oh, between JWST
And
and
Roman.
Roman.
Yeah.
Both. They're these complementary things. JWST is the best tool that we have and will have for at least 20 years, for studying the atmospheres of individual planets. There's no way we can match its precision with any other telescope. Roman is will help us find new planets. It will help us find planets that are literally impossible to discover with any other telescope that we have on Earth or in space. And so those are different tasks, and they're both necessary towards this long-term goal of finding really Earth-like planets. We need to find more planets. We need to study atmospheres so that we can kind of project out to, oh, let's find a planet that is really like Earth and study its atmosphere with some future telescope.
I've heard in pop science articles that there's a few exoplanets out there that are particularly exciting to be looking at right now with respect towards finding life
Yeah,
on these exoplanets. For example, K218b,
yeah.
just one of those
Oh, that's a yeah.
random, seemingly random names, but yeah,
That's a spicy one.
it
Yeah,
is apparently a really spicy topic
yeah.
among astronomers and scientists right now. That and the news seems to be kind of misinterpreting some of the science a little bit. Is that true?
I was actually really pleased with some of the news coverage I saw on K2-18b.
Good.
This is, I guess I get a lot of my science news from NPR, and Nell Greenfield Boyce did her first article on this was, here's this really exciting thing, but there are lots of very serious doubts about it, which is so true of so much science. And so that was it was nice to see that right up front, that it wasn't this exciting conclusion, period. It was, maybe there's something exciting.
Hmm.
Let's qualify that.
Yeah. So what is this exciting thing that
I'm
we
not going
might
to
have
tell
found?
you. It's in this.
Oh.
Yeah. All right. So the claim for K2-18b. So this is the 18th planet that was discovered by K2, which was the Kepler-2 mission, which was the repurposed Kepler spacecraft after one of its reaction wheels broke, and engineers need to figure out a new way that it could observe the sky for a remaining few years, which allowed this very impressive NASA telescope to continue observing for a few extra years, and found this planet as the 18th out of this rebooted mission. So K2-18b is a planet that is about the right temperature to be habitable, with air quotes around it, meaning you could imagine liquid water near its surface. It's not too hot and not too cold. The weird thing is, it probably doesn't have a surface. It's big enough and its density is low enough that it's not a rocky planet like Earth with a thin atmosphere. It is either a just very gas rich planet that's more like Neptune, or it's been theorized maybe a planet that is has 1,000-kilometer deep oceans with a gaseous layer that's on top of that. And so it's very different from Earth, but it's a place where maybe hypothetically, if we stretch our imagination, you could imagine life. So that's all theoretical. JWST observed K2-18b a few times, and there have been, the claim that was made here was that there were absorption features seen in its atmosphere that indicated molecules, dimethyl sulfide and dimethyl disulfide, that maybe potentially could be interpreted as biosignatures, as indicators of life on there. So maybe we found aliens on other planets. That's the claim.
Great. Okay, that's different than the news I was seeing. I
Okay.
get I see some news on Instagram and it's
Yeah.
like, we found aliens. Elon Musk is one of them.
Yeah, okay.
Of course, all of those.
Yeah, gotcha.
And, but yeah, so that's good to hear that you're happy with the way that a lot of the media has been portraying science. So there may be life on this planet, K2-18b, but that may not be the only conclusion. What is the other potential conclusion if it's not life?
Yeah. So with the initial publication of the paper, there was a little bit more circumspect about is this life or not? But the initial publication of that was greeted with some skepticism. Like, if you called up lots of astronomers, they'd be like, "Well, I have some questions about this. I'm not quite sure about this." And then there was this amazing process that happened, that within a week, a few other scientists, independent groups, went and worked with the same data that the first group worked with, analyzed it again using independent methods, and independently assessed the statistical significance of the result. They went and looked at the data themselves and saw that this is a NASA telescope. All the public's data, the data is public to everyone. They went and looked at these data and said, "Oh, the statement that you're making inflates the significance of this. If there are lots of other hypotheses that could match this data as well, you could explain these data just as well with clouds in its atmosphere. You don't need these weird molecules, dimethyl sulfide." Or they found other molecules that were even weirder that could also explain the data. And so it was this wonderful example of the scientific process and scientific community at work, that we're all working together to try to figure out, to try to do this cool, hard thing of finding life on other planets. And so it was not trusting any one individual source, that this extraordinary claim needed to be tested and validated. And so as soon as other astronomers started working on that, they're like, "Oh, no, this isn't happening." And I think I'm pretty sure that JWST will observe the system again and we'll get better data and we'll get a more refined answer on what actually is going on in the system. I personally am very skeptical that there's evidence for life on there. There could be life there. I don't think we've seen evidence for it yet.
I remember I was in my research methods class
Yes.
when this data was coming out and it was popular and new, and my professor actually showed some data that you made, just a random line of data that you fit to the data that they saw.
Hmm.
And with that you proved that like this doesn't necessarily mean that there's life on this planet. Like we could come up with many different explanations of what's actually happening.
Right.
And I think that's such a beautiful part of science. So few things slip through the cracks when it comes to a whole bunch of people who dedicate their lives to figuring out what the truth is.
Yeah.
And that your success as a scientist is based on how good you are at finding the truth and how efficient you are at doing that. So scientists, when data comes out, a lot of scientists just jump on that and start saying, "Well, is that really true? Or can I retest this?" And everybody's very skeptical when science comes out. Yeah, I think that's beautiful.
I agree. Maybe to add one thought, I remember in grad school, one of my professors shared this idea that I really like, that there's no perfect paper. Like, then this is talking about like scientific journal articles, that you're not going to write something that is absolutely perfect. And so that's both like kind of relieves the stress a little bit, but it points out that our responsibility as scientists is to explain what we've done as best we can, to make the data that we've collected publicly available so that other people can analyze it as well, and then trust that having a rich, vibrant, well-funded scientific community out there can check our work for us. So we do our best to like make the most exciting, honest, accurate claims we can with our data, but we can also trust that our colleagues will be there to make sure that we're being honest and that these results are real. So that the evidence we have doesn't rely on trusting any one person. It relies on trusting tradition of testing theories against data, and that keeps working over
Yeah,
and over again.
yeah,
So,
absolutely. Okay, so we have K2-18b,
yes.
and it's been a very hot topic lately. What are some other exoplanets that are on your watch list right now? Like,
Ooh,
which ones are most exciting to you?
yeah. Well, if I can plug some of our work myself, one planet I really like is LTT 1445AB. This is star number 1445 in Luyten's 2/10 catalog that was compiled decades ago. It's the primary star in a triple star system. So there are two other stars that are orbiting around each other, orbiting around this star. And this planet is orbiting around the primary star. So LTT 1445AB is a rocky planet that's a bit bigger than Earth. So it's a super Earth. It's a bit hotter than Earth. It's sort of like it's close enough to its star that it receives the same energy that Mercury receives from the sun. So it's a hot planet. We're not thinking about this as being habitable. But it's a really good test case for this question of what does it take for a planet to retain its atmosphere, especially around a small star like this one. LTT 1445A is an M dwarf, these tiny stars that are really tempestuous. It's a system where we can look at this planet and say, ask a question that is something like, ooh, how much bigger would we need to make Mercury for it to have the gravity to retain an atmosphere? Or like, how much closer would we need to push Venus towards its star so that it loses its atmosphere? And so we observe this planet with JWST to try to answer whether or not it has an atmosphere. We used infrared wavelengths of light to measure the surface temperature of the planet. And we found that the temperature of the planet was consistent with it not having an atmosphere. It has no greenhouse effect, or like we don't see evidence for a greenhouse effect on it. We don't see winds distributing heat around to its night side. We're pretty sure it doesn't have a really thick atmosphere on it. And so it's a planet that is like it's one of thousands of transiting exoplanets that are out there, but it's one that pushes us a little bit closer to a more complete understanding of what does it take for a planet to retain an atmosphere around a star.
Cool. So it's going to be teaching us a lot about future
I think so.
exoplanetary stuff,
Yes. Yeah,
hopefully.
yeah.
Okay, well, that's awesome.
Yeah.
That's awesome that your team was able to see that.
Yeah. Yeah, we know it doesn't have a like kind of Venus-like atmosphere. It could still potentially have a like a thinner kind of Earth scale atmosphere,
Okay.
but we'll need more observations to tell.
Okay. So with exoplanet research, how is it important to figure out that an exoplanet doesn't have an atmosphere, or to go look at K218b and learn more about its atmosphere? How does that at all affect us on
It doesn't.
Earth?
So I'm going to qualify that. It
Yeah.
does deeply. But
Yes.
in
Yes.
some sense it doesn't. It doesn't in the sense that these planets, exoplanets, are so far away, we are never visiting them. We're not visiting them in our lifetimes. We're not escaping to them if we destroy Earth. These are things that are just really abstract and far away. They're worlds that each individually by itself exists out there. It's like nice and powerful to be able to look up at the sky and to point at stars and say, I know that there are planets around there. I know what those planets are like. But that's doesn't have a like practical, tangible purpose for us here on Earth. What does matter for us is understanding how atmospheres work. We have three terrestrial planet atmospheres in our solar system. There's Earth, there's Venus with this thick atmosphere with this strong greenhouse effect and like blazingly, scorchingly hot surface temperatures. There's Mars with this really weak greenhouse effect, this very tenuous atmosphere. And there are other there's like Titan around Saturn kind of has a
Mhm.
terrestrial planet atmosphere. But we have a few examples in our own solar system. That's not enough for us to understand everything that goes into how planets evolve, how their atmospheres evolve, how their atmospheres respond to different conditions. And so why studying exoplanet atmospheres matters to me, selfishly, as a little earthling living on our planet, is I want to have a better, like, physical understanding of how planetary atmospheres work. And one of the tools that we have for that is studying exoplanets to understand how atmospheres respond to all of these different conditions so that we can continue this march forward of observations and theory continuing to improve our understanding of the universe around us, both for its own sake, because I think that's just like fundamentally sort of a moral thing. As intelligent creatures, it's our job to understand the universe a little bit better, but also as a practically selfish thing that we're here on our little spaceship Earth. It is our job to take care of this planet, and every piece of information that we have about how to take care of a planet is going to help us do a better job of it. And so that's why I want to keep studying exoplanets, so that I have this more powerful lens to look back at Earth with.
I really like the way that you told me before we started recording that you kind of treat this as like your own little laboratory with experiments. So if you wanted to find an exoplanet in a certain condition, like say, hey, what if we found out a Mars type planet that was closer to the sun or further away from the sun with new missions like JWST and Roman, we will be able to hopefully, ideally, find a system where that actually exists, and we can see how those types of planets react in those situations, and therefore, just like you said, learn more about what planets are and how they form and how they evolve, which to me immediately, tangibly helps us to understand solving the climate crisis or any other type of understanding of weather and how weather on Earth will evolve through time. Like you said before, planets are always changing, our atmospheres are always changing. That is a normal part of it.
Mhm.
But understanding it will help us a lot more to prepare for changes or to prevent them.
Yeah, yeah, exactly. And if I can add to that, the like, it's hard to predict how science is going to be useful. when I was when I was in your shoes, when I was an undergraduate student, we had discovered a few exoplanets. They were all hot Jupiter exoplanets. They seemed like weird oddities. My professor seemed sort of skeptical of them. There was like, I guess these things exist. And then now, what, 2 decades later, um, it's not just a few weird hot Jupiters. It's thousands of exoplanets that have been discovered through the tireless efforts of NSF and NASA funded scientists using ground based telescopes, using the, the European Corot Space Telescope, the NASA Kepler Space Telescope, the NASA TESS Telescope, analyzing those data using a whole suite of instruments on the biggest telescopes that we have on Earth to study these planets in more detail, using Hubble and using JWST. That right now I'm here talking about climate on rocky planets around other stars. And I like really deeply do not know what amazing things we could be doing 20 years from now if we keep doing science. The only thing that I know is that if we hadn't had those missions, if we hadn't had scientists working so hard on trying to learn more about finding more exoplanets and studying how they work, we wouldn't be here. And so it's hope for the future that seemingly impossible things become possible in time. And it can be hard to see that path forward, but we definitely won't get there if we don't try.
Great. I think that's a beautiful place to wrap up. I think that was great. Is there anything else that you'd like to add? Okay,
Wait, can I ask you a question?
absolutely.
Why does studying exoplanets matter to you?
Oh, exoplanets is one of the first things that ever got me excited about astronomy. Actually, is
Oh,
when I got into astronomy, I was like, yes, I want to know everything there is to know about exoplanets. And that to me is because just like art for a lot of people is so important to them that it is the only important thing to them. It's what they dedicate their whole entire life to. And luckily that benefits a lot of other people that consume that art. And it's like this existential need for some people to consume art. Art is very emotional. Science does the same thing for me as art. Just knowing what conditions could exist like in the universe, knowing how big our universe is, even if I can't comprehend it, just being baffled by such things, that awe, that wonder it's the same thing fundamentally to me as what art is for a lot of people. Um, to
yeah,
know
I
that
agree.
an exoplanet could potentially have life on it, or even if it doesn't, to know that Titan has lakes of liquid methane, or Europa may have or likely has some subsurface oceans, and maybe there's space whales swimming under there. Probably not, but but just letting our imaginations run wild with that, and as technology progresses, allowing us to know even more details about these things is so important to me, and it's something that I'm willing to dedicate my life to as well, just like somebody painting or playing the violin.
Yeah. Yeah. Oh, that's so beautiful. I love that. Yeah, and I love this like as like places or opportunities for our imaginations to run wild. But as you said it, it's like it's kind of like it's imagination constrained by nature, right? Like that it's imagined like maybe there are space whales on in Europa's oceans. We can go test that
Yeah.
by going there and asking that question and figuring out evidence either way. It's just like yeah, it's such a like cool, powerful form of art that we can imagine these incredible things and then figure out whether they're real or not.
It makes to me it makes life worth living.
Yeah. Yeah,
Yeah.
absolutely.
Yeah. Great. Is there anything else you wanted to go over?
No.
Okay. Great.
I
Zach,
kind of
so
wish
I've
I
got something.
interviewed you in a podcast.
No,
This is
I'm too
you're good at this.
existential about
Great.
everything. Yeah, thank you so much, Zach, for coming on the podcast. I've really enjoyed talking about all of this, and I look forward to hearing more about what your team does in the future.
Absolutely.
Yeah, and I hope to have you on again sometime.
My pleasure.
Great. All right, and thank you to our viewers for tuning in. This has been another episode of the Open Orbit podcast. You can find us on our socials on Instagram and Facebook, and we've been broadcasting live from KVCU studio at CU Boulder. Stay tuned for another episode.